Okay, let's get started. It occurred to me that I'm throwing around a lot of terms that I've never explicitly written down definitions for. So let's get clear on terminology at the outset here. So we call this terminology of chemistry. You can just continue on what you were. Okay.
I don't think your
What?
mic's on.
My mic isn't on?
No, it is on. It's fine.
Okay. Still trying to find a marker that writes, but that's a little better. Okay. And some of this will be review, but some of it won't. So let's just start at the beginning, though. I started out defining elements and compounds some time back as pure substances. Well, let me start out by, I'm not sure I ever wrote down a definition of what I meant by substance. So let's start with this statement. All samples of a substance have identical chemical and physical properties. Okay, now, what does that mean? That means if you take pure water, if you do electrolysis on it, you'll always get, the same amount of the ratio of hydrogen to oxygen, right? I mean, that's a chemical, that would be a chemical property. But if you do something simple like boil it, okay, every sample of water that you take will always boil at the same temperature, right? So, I mean, will always freeze at the same temperature, okay? So all samples have identical chemical and physical properties. If that isn't true, what do you have instead of a substance, Troy?
A different substance?
Well, yeah, I mean, you have a, Neve, what were you going to say? Daniel. Well, no, when an element would satisfy this criteria, right? What I'm thinking of is a mixture. Okay, so if you have, a lot of the things that we see around us are not pure substances like this. They're mixtures of substances, and their properties will vary from sample to sample depending on the exact proportion of the stuff making them up, right? So so let's define, so that's, this statement defines what a substance is. Let's define a mixture. A mixture is two or more substances each of which retains its specific properties. Okay, so let me give some examples. Ocean water would be a mixture. Now, how do you know that, Daniel?
Because it's water and salt.
Right, and you could, for instance, boil off the water, evaporate the water, and what would be left behind? Some salt, right? So you can separate it into those two substances. Now, once you've separated it into those two substances, the water is a pure substance, and it's just like every other batch of water that you can have. And the same thing with the salt. It will be, actually the salt in ocean water is regular table salt. It's made up of sodium and chlorine. Sodium chloride is what it's called. And it's going to be exactly the same as every other bunch of salt that you find. Okay, so let me see. Well, another example in in nature, sometimes you find iron ore that's mixed with sulfur. And you can actually, if you pulverize it, you grind it up, you can actually separate it with a magnet, because the magnet will attract the iron ore and leave the sulfur behind. So, there's a case where you've proven you had a mixture, right? What about milk? You think? What would you call that? Is that a compound? Is it a mixture? In other words, is it a substance or a mixture? You think it's a pure substance? Hmm? Yeah, it's a mixture actually, because yeah, you could. I don't think it would be easy necessarily, but I'm sure they could do it. Sure.
Is non-fat milk also a mixture, or is it?
Yeah, I think non-fat milk would be a mixture too. It's got a bunch of things in it, but for instance, in milk, one of the things milk has in it is water, right? If you boil milk, for instance, you'll change its chemical properties, because you'll boil off some of the water in it, and the stuff that's left behind will be thicker, and so it's definitely, milk would definitely be a mixture. And we talked about other mixtures earlier in the class. Gunpowder, for instance, made up of charcoal, saltpeter, and sulfur. So it's a mixture of 3 different things. Okay. Now, it's important to have this distinction between pure substances and mixtures. Now, pure substances fall into 2 different categories, right, that we've talked about. I think I might have written this up on the board before, but it's worth writing again. An element is a substance that cannot be, what's my next word?
Broken down.
Yeah, decomposed. And I'm going to add the qualifying, this is the basic idea. I'll add the qualifying phrase, though, by a chemical change. Later, physicists will figure out how to break down elements by other ways, but you can't do it by chemical reactions. Okay, then a compound is a different kind of, It's also a pure substance, but it's composed of two or more elements. So a compound is a substance composed of two or more elements and it can be decomposed into its elements by chemical reactions. Okay, now I've got a couple more terms for you. I don't know whether I've defined what an atom is yet, but okay. See, these, until chemists got clear on these concepts that I'm listing for you here, they really couldn't do chemistry. I mean, Lavoisier was the first to get perfectly clear on all these concepts and figure out an objective way of distinguishing elements from compounds, right? And that's when chemistry really started. And then they still didn't have a physical theory that allowed them to understand these thousands of different reactions that they were looking at. And that was the atomic theory. They had to come up with good definitions of what an atom is, which was lacking before, because when the atomic theory started back in ancient Greece, remember, the idea was the atom is the ultimate indivisible particle of matter. Well, I mean, how do you know when you've gotten there? How do you know when you have an atom? And the Greeks had no answer to that question. Well, scientists in the 19th century, before they could really work with the atomic theory, had to be able to answer that question. How do we know? So they came up with a definition of what an atom was that differed from what the Greeks would have said. So let me give you that. An atom, okay, I'm going to try another one here. An atom is the smallest particle of an element I'm going to get lucky one of these times. Smallest particle of an element Thank you. That can, I don't know, you tell me. Can you read it any better from back there? I could try green. How's that?
Just push it in, push it.
Oh yeah. Let's see if I can get the green to work. Okay, the smallest particle of an element that can enter into a chemical combination. Ah. So the mistake I was making was I was just fixated on black there.
This one's definitely.
Okay. Now, do you see how this definition is different than what the Greeks would have said? Because the Greeks were referring to atom as the ultimate indivisible particle that can't be broken down by any means. Well, like I said, I mean, how do you know when you get there? Yeah. Ben.
Also, if we're made out of atoms, then if like cut something, wouldn't we be cutting atoms?
Oh, well, they would say, well, you're not cutting you're not actually splitting apart the atoms. You're just, in effect, cutting between the atoms and separating. So you haven't, I mean, the thing is, you need a lot of evidence in order to make a claim like, okay, we've reached the ultimate particle here that cannot be broken down by any means. I mean, now that we know about nuclear bombs, for instance, you could say, well, can it be broken down by, if you drop a nuclear bomb on it, will that break it apart? Well, it turns out, yeah, it will in some cases. So these atoms that the chemists are talking about are not completely indestructible. But that really wasn't what was needed. I mean, you can't know you have the ultimate indestructible thing until you have a lot of scientific knowledge, until you're at a very advanced stage. At the beginning here, what they needed was, in effect, the chemical atom. The atom from the point of view of chemists, which is an atom that can't be broken down just through chemical reactions. Okay, so that's in fact exactly what they needed to define as what is meant by the term atom. And that's what they finally did in the 19th century. Now, and examples of atoms. We have seen oxygen, hydrogen, nitrogen, carbon, chlorine. Yeah, that's good enough. Now, there's one other term that I started to introduce this morning for the first time. Evan?
Molecule?
Yeah, molecule. Okay, so what do you think a molecule is?
Wait, what's C?
Neat.
Combination of many atoms grouped together.
Yeah, bonded together. Now that would be one way to describe it. The chemistry book I have, maybe that's even better way than what I've got written down here. Let me see. Well, I guess this is a little more precise in some ways. My chemistry book defines molecule as, let me see, molecule is the smallest I don't like this definition. I like Neves better. I'm going to use Neves. A molecule is let me see, let's just say two or more atoms bonded together just leave it at that. So what would come under this definition is a few different things. You could have a pure elemental gas, for instance, pure oxygen, okay? But we would still call them oxygen molecules rather than oxygen atoms. Why? Evan?
Because when they're floating around in the oxygen, they're two of them joined together.
Yeah, exactly. Because what you have, if you have a gas of oxygen, you don't have just a bunch of oxygen atoms like this. You have them paired up and bonded together like that. So, so this is, you would still refer to this as a molecule. So O2 is a molecule, you know, H2, N2, but also more complicated things like we've seen. For instance, the ammonia gas that we talked about was NH3. The fixed air that Black discovered way back in the 1750s is carbon, CO2. Okay, now let me see. I need to I need to talk about this notation that I'm using too and make that explicit. So have you got these down now in your notes? Okay. Now, here, let me just all right, I've been using certain notation in chemical reactions here, and let me make it explicit. When I, for instance, write, let's say we have N2 plus 3H2 goes to 2NH3. Now, do you all know what that means? Okay. What it means is, see this lead coefficient out here, I'll just make it explicit and write in the 1 here in front of the nitrogen. These numbers here are coefficients telling you the number of molecules in the in this reaction. Coefficient identifying the number of molecules. And then these subscript numbers, the subscripts identify the number of what? Evan.
Atoms.
Number of atoms in the molecule, right? Okay, so what this means, I mean, you could do this. Let me just write out this reaction now in if we just do it in picture form. So I have one nitrogen molecule, which means there's a nitrogen atom bonded to another nitrogen atom, right? Then I'm adding to that three of these hydrogen molecules that are that each consist of two atoms. Okay, so all these things are going now to recombine in a different form. And I'm going to create
Is that N minus N, H minus H?
it's no, it's N hooked to N,
Oh,
H hooked to H. Okay, yeah, sorry, maybe here, if we put, is that, I don't know whether that makes it any clearer. So, I mean, what ends up happening in this reaction is, you know, these nitrogens get split apart. And each one of those nitrogens grabs three hydrogen atoms to surround itself with. And lo and behold, you end up with a gas that has totally different properties. I mean, this ammonia gas that has that strong smell that you've all smelled from cleaners. But you should look at, I mean, see, this is what, in this long-winded version that I've written here in pictorial form is what's going on. But you need to compare, you know, this with this equation that's much simpler to write to see that they mean the same thing. Okay? Okay, so I can write these kinds of equations now without throwing anybody? Nobody's going to get confused? Okay.
so like 1 and 2 equals, well, 1, there will be one molecule of that.
Yeah, I mean, this is one molecule, okay, because it's two atoms, but they're hooked together. And in the presence of hydrogen, if you if you put it under high pressure, under the right conditions, you can get these two nitrogens basically to split apart, and each one of them ends up grabbing three hydrogens, and so you end up with this over here.
Like plus that? What is that?
Oh, it just means you have two of these ammonia molecules. Now you have to have two, because see, each ammonia molecule has one nitrogen in it, and you started out with two nitrogens. So you have to have, I mean, there's no appearances and disappearances of atoms in chemistry. You know, whatever number of atoms you have on one side in the reactants, you have to have in the products. Okay, so okay. Now, well, let me just finish off the main law that I was explaining to you this morning, the law of combining volumes. And I don't think I ever stated that explicitly. So let me do that. Okay, so what this says is the volumes of gases involved in a reaction can always be expressed as a ratio of small whole numbers. Okay, so that's just a precise way of stating the idea that we saw this morning, that gases always react in these integer ratios of their volumes. And the explanation for that, obviously atoms have to react in integer ratios. So when chemists discovered this, that led them to the idea that there's this direct one-to-one relationship between number of atoms and volumes. By the way, the guy who discovered this, I should tell you his name. This is Joseph Gay-Lussac in 1808, a French chemist. Now, in a way, Gay-Lussac here kind of missed the boat, because he came up with this this wonderful law. I mean, he was a great chemist, but he was very well, he wasn't really a theorist. And you know, we've seen lots of times in science before that you need not only to do good experiments, you need theory too, to really make a science. So the guy who actually came up with the theoretical idea in this case was an Italian chemist, Amadio. Does anybody know his last name? I bet you've heard of him before. Some of you might have heard of him. Avogadro. Anybody ever heard of Avogadro? No? Okay. But he's the guy who came up with this idea that equal volumes of gases, so let's just call this Avogadro's law, which says equal volumes of gases contain equal numbers of molecules. And that's exactly the idea that was needed in order to give a physical explanation of why this law of combining volumes is true. Evan?
Just the pressure and temperature, does that matter at all?
Oh, it does. He takes for granted, I mean, in this statement of the law, I've taken for granted that the gases are at the same pressure and temperature. But you can, that's a qualification you can throw in. So you can say, at equal pressures and temperatures, equal volumes of gases contain equal numbers of molecules. Okay. Now, I mean, if you knew this, of course, you could predict in advance that this would have to be true. Oh, by the way, Avogadro came up with that idea in 1811. So just a few years after Gay-Lussac stated, his experimental law. Okay. That's pleasant. Let's. All right, I want to tell you about a different discovery, or start into telling you about a different discovery that gave yet more chemical evidence for the atomic theory. And this was in the 1820s. Well, actually, it started in 1814. I'll give you the first discovery that, and you tell me why this is evidence for the atomic theory. Okay, it was by this guy, same chemist that I've told you about before that discovered laughing gas and chlorine, Humphrey Davy. He had an interesting idea in 1814. He decided to burn a diamond. I don't really suggest doing this at home.
Don't you get cardboard or something?
Yeah, you're way ahead of the game here. Here's what Davy did. He took some diamond and he put it in a glass container, and he pumped all the air out of the container. Okay? Then he took this huge magnifying glass that he had and shined it on that, shined a whole bunch of sunlight right on that diamond and just kept heating that thing up. Well, it turns out that a funny thing happens when you reach about 1,000 degrees Celsius. The diamond disappears, and it turns into graphite. I mean, the stuff in your pencils. Okay. That's right. Now, if you could go the other way, you can be a rich man if you can figure out how to take that pencil lead and change it into diamonds. It turns out that what Davy did is less lucrative. I mean, to take diamonds and turn it into pencil lead. But yes.
Yeah, all you have to do is just take a piece of graphite
I see that look on your face,
and
and your mom's going to kill me when you go home and take her wedding ring and torch it with a big magnifying glass. Yeah, you didn't get it here, but yes, that does work. You can take a diamond and turn it into pencil lead. Yes.
So our pencils are all worth like thousands of dollars.
If you could go the other way. Now, it turns out you can go the other way, but it's extraordinarily expensive. You can take graphite and under extraordinary pressure turn it into diamond. But it costs way more than the diamond is worth. So no, it's not a commercial process.
Do you freeze it or something?
You can, but all you get is frozen graphite. Rachel, did you have something?
I was just gonna ask if it was possible to change it back the other way.
Oh, yeah. Yeah, it was first done, actually, I think, it was in the 1900s. I think it was around 1950 that somebody first actually turned graphite into diamond. But like I said, you need super high pressures, and it's such an expensive process that it's not practical. Ben.
So, like, you just put it under a lot of pressure and it turns back into a diamond.
Yeah. Now,
Airplane?
yeah, you squeeze it really, really, really hard, and you can get it to go into diamond. Now, what is this? Does this suggest anything to you? I mean, this is pretty strange when you stop and think about it. I mean, you look at diamond and you look at what's in your pencils. They look really different, right? You would think these are completely independent substances with totally different chemical natures. And it turns out they're both made of the exact same stuff. And that stuff, I mean, as Daniel said a minute ago, it turns out to be carbon. You can actually burn diamond and graphite with oxygen and get carbon dioxide. So, I mean, chemists figured out that not only they're both the same stuff and they're both carbon. Now, how can carbon be in such two completely different forms? Neve?
Dense this.
There is a difference in density. But if you think in terms of the atomic theory, does anything come to mind that might explain this? Troy?
Different formations of the atoms?
Exactly, because the atomic theory has this potential that not only does the material itself make a difference, but the exact way that it's arranged. And so you have not only the stuff, but also the structure that the stuff is in to work with in your explanation, and I'll show you what that means next time.